Hello and welcome to yet another lecture on Basic Electrical Engineering, paper code ESEE 101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is continuous and discontinuous current mode of operation of buck converter. Lesson objective. After the end of this topic, students will be able to understand the working of buck converter for continuous and discontinuous current mode. So, we have in our previous lecture, we have seen the basic operating principle of buck converter. Now, we will consider another two mode of operation that is called the continuous current mode of operation, and that is the discontinuous current mode of operation. From the name it is clear that for that particular, this is called the continuous current mode of operation. So from the name it is clear that there is no discontinuity in the current. So current will remain continuous. So this is the general voltage and current waveform for the buck converter for the time t1 and the time t2. So it is clear that if the output voltage versus time graph, this is when the switch 1 is on, this is when the switch 1 is at off condition, and again when switch 1 is on. This is the general output voltage waveform that we have already seen in case of the buck converter. The general voltage output voltage waveform for the buck converter. Now, for the time period, this total time period is T, and the converter is or the switch is on for the time period T1 and switch is off for the time period T2. Now, this is the output voltage. The output voltage during the time for freewheeling, the switch SW1 is off. This is known to us. So, it is provided by the drop across the R, across the load resistance R due to the decaying induction current. The respective current waveform shows in the figure B, that is, so this is the current, that is the ID current or current through the inductor, current through the decaying current through the inductor, or we can say that current that is flywheel through the diode. Means when the switch is off, the diode D1 is on, and the current through the diode D1, say when the switch is on, that particular part, there is no current through the diode. At that particular instant, the diode is act as a reverse bias circuit. But when the switch is off, the diode is on condition and the current through the diode is decaying in nature. Again, the switch, this is the current nature of the current through the diode. When the switch is off condition, that is mean the diode is in on condition, and we are commenting on the freewheeling effect of the diode, followed by again the current through the diode is 0 because the switch is on, and again when the switch is off, this is again the switch is on, the current through the diode is 0, and when again the switch is off, the current through the diode is decaying in nature. So, if we assume that no resistive component of the inductor has no resistive component and no drop across the diode. So, this figure that is C, that is represent the input current waveform, that is the input current waveform, that is the input current waveform, and this is the output current waveform. The input current waveform will be same as the input voltage. This is the input current waveform that is already seen, because the input current will be obtained for the on time of the switch, and this is the output current. And it is clear that the output current, that is when the switch is on, it is going from a minimum value to the maximum value. And again, when the switch is off, that is diode is on, it is again come back to the or it is again come back from the maximum value to minimum value, and this will continue. It will repeat it. Means when the switch is on, the output current that is going from a minimum value to the maximum value by following that path. And when the switch is off, that means the diode is on, it will again come back from the maximum value to minimum value. And this path, this is repeated in nature. So, the voltage drop and the induced voltage of the inductor is seen by the graph, that is V in minus V0. That is the graph when the voltage drop and induced voltage of the inductor. This is the general graph, that is V in minus V0. So this is the voltage and current waveform for the buck converter for T1 and T2 time. So we all know for the buck converter, the average output voltage, that is V average, is equal to V output is equal to V in into D. D is the duty cycle that is known to us. So the power output, that is the output power, P output, it is equal to V0 I0, or we can write it is equal to V in I in, that is the input power, that is P in. So from that particular equation, we can calculate that I0, it is V in by II by I0, V in into II by I0. That is, we can comment that it will be II V in D. That is, we can write that that will be I0 equal to II by D. So, from the graph we have obtained that during the on time, during the on interval, the buck converter, the output current I0 is the same as the input current II. It is clear from the during the on time that output current is same as the input current. The output current, that is the input current, and the output current both are same. During the on time, that is the output current nature, and this is the input current nature, both are same. When the switch is off at the time period T2, the output current I0 drops from its maximum value, that is I max, to the final value I min. It's clear that it will fall from the time period T2 when the switch is off. This fall from I0 will fall from a maximum value of I max to I min. So during the period of T2, current flows through the inductor, the load resistors, and the freewheeling diode D. This is known to us as the current falls to a value of I mean. It means that the switch is closed again. Diode current stops immediately, that is known to us, while the current supplies to the load from the source is not I mean. That when the switch is again closed, that is the diode current. That again, when the switch is closed again, the diode current again falls and it goes to the zero value. It's clearly seen from the graph. The current starts increasing during this conduction period and it is again attains a value of I max. Again current start conducting and it is going to the value of I max. Again it is following the previous steps. From I min it is going to I max. So the current start increasing that I have told. As the current attains the I max, the switch again immediately reopens and this process follows. Repeat it. The load current start decaying and the freewheeling action will start, that is known to us. So the load current that will oscillates in between I max and the I min. So the average value of the load current, that is, or the inductor current, that is the average value of the inductor current, that is IL, equal to summation of I max I min by 2. So we all know that IL nothing but the output current I0, it is equal to output voltage V0 by R. So if I equate the both equation, we will get an equation like that. That is I max plus I min equal to, from that particular equation, we will get the equation that is I max plus I min equal to 2V0 by R. So we all know that the voltage across the inductor, that is VL, equal to V0 equal to L ddt of I0. So we can write that ddt of I0 from that equation is equal to V0 by L. So change in I0, that is V0 by L, and the change in T. So the switch that is open for the T2 interval. So with the switch open for the T2 interval, so change in I0, that is change in current, that is I max minus I min, is equal to V0 by L into T2. So that from that particular equation, we will find the change in current, that is I0, that is equal to V0 by L of change in time, that is del 2. So what is the change in current? Change in current can be written as I max minus I min, and the change in time can be written as T2. So this is one equation, this is another equation. From that two equation, we can find the value of I max and the I min. This is the value of I max and this is the value of I min. But I max is equal to V0 by R plus half of V0 by L T2, and while I min is equal to V0 by R minus half of V0 by L T2. So the peak to peak ripple current, that is equal to, that is the difference between maximum and the minimum current, and that is equal to T2 into V0 by L. So it is observed from the waveform that the I0, that the output current always flows through the load for both T1 and T2 intervals, and hence thus the operation is called the continuous mode of operation. If I observe the waveform, if I observe the waveform of the I0, yes, it is going from a minimum value to maximum value, then it is again come back to the minimum value, and this process is a repeated process. But we can say that the there is a continuous mode of operation. There is no discontinuity of the output current. So this is the output current that we are obtaining, and it is going from minimum value to the maximum value. And this is a continuous mode of operation. If I see from the graph, so this is called the continuous current mode of operation of buck converter. So this is known as the continuous current mode of operation of buck converter. So another part is the discontinuous current mode of operation. The another mode of operation is known as discontinuous current mode of operation. So in this case, the duty cycle B, that is low, or the value of the inductance is lesser. If the value of the inductance that is lesser, the load current decreases during the off interval T2 and may reach 0 during the off period of each cycle. If the value of the inductor that we have considered, if the value of the inductor is less, or so whatever we have seen in the previous case, that the current is going decay in nature, but it is not. But here, if the value of the inductance is lesser, the current may reach to the zero value during the off period of the each cycle. The current again builds up from 0 during the T1, that is on period. So here, if our previous discussion, previous continuous mode of operation that we have seen, that current is not going to the zero value, so it is called the output current, it is called the continuous mode of operation. But in case of the discontinuous mode of operation, means there is a chance of the current, if the inductance value is less, then the current may reach to the zero value when the time T2 is during the time period T2, when the switch is off, and when the switch is on, again it starts from the zero value during the time T1 period. So the load current that is said to be a discontinuous in such mode of operation. So this is the voltage and current waveform of discontinuous mode of operation, where the output voltage remains same. But it is clear that with the help of the dotted line, that is indicates the discontinuity of the current for the low inductance value, but the bold line that is indicate the continuity of the current. So there is a chance, it is clear that the diode current is going to the zero value. In our previous case, it is clear that diode current is not going, if I see our previous case, there is a diode current is not going to the zero value. Diode current is decay in nature, that is current through the inductor that is decay in nature, but it is not going to the zero value. But in this case, if the inductance value is less, the current will be go to the zero value. The current will be decaying in nature and it will go to the zero value. This is the switch is on, diode is off. Here the switch is off, diode is on. Again the switch is on and the diode is off. And this process is repeated, where the input current is gradually increasing, but the input current is gradually increasing. But the input current is gradually increasing in nature. And this is the nature of the output current. This is the nature of the output current. There is a chance of the output current to go to the zero value. So the dotted line that indicates the discontinuity of the current due to the low inductance, and the bold line that is indicate the continuity of the currents through the final decaying current that is touches the zero value. This is for the I0 output current. There is a chance of the I0 current to go to the zero value for each interval. That is voltage and current waveform for discontinuous mode of operation. So that is means for the discontinuous mode of operation, the I minimum value of the I that is going to the zero value. So if I equate that I minimum value with 0, we will find the value of the inductor, that is L equal to T2 by 2 into R. Hence, to have a least amount of discontinuity, the value of inductance must be greater than T2 by 2 into R. The installation of inductance with higher values provides almost no discontinuity of current and is desirable for equipment operations. Moreover, with higher value of inductance, the peak-to-peak repel of the load current that is reduced. Theoretically, with a high value of inductance, the load current should be repel free. So we will now discuss about the value of critical inductance in another form of representation. The critical inductance, that is LC, is the value of the inductance that is in series with the load for which the output current falls to zero at time t equal to t during the off period of the buck converter. If the current variation from 0 to Imax during the on period and the variation from Imax to 0 during the off period is taken as a linear to be linear, the average value of the output current is given by that particular equation. The average value of the output current is given that I0t is equal to half of Imax T1 plus half of Imax T2. That is half of Imax T1 plus T2, or we can write that half of Imax T. So Imax is became 2I0, that is the maximum value of chopper current at T equal to T1. So it may be noted that with the converter on, that is the output voltage is equal to V0 plus L di dt, that is equal to Vi. Or we can write that V0 plus L I max by T1 equal to Vi, or L 2I0, that putting the value of I max here, that is 2I0 by T1 equal to Vi minus V0, or we can write L equal to Vi minus V0 into T1 by 2I0. This is the value of L. However, the average value of the output voltage may be expressed as, that is V0 equal to F T1 Vi, that is known to us, but the output power will be given as P out, that is equal to V0 I0. So the basic conception of discontinuous mode of operation is deal with the when the switch is off, if the inductance value is lesser, the current that is decaying in nature to the inductor will reach to the value 0. And again it is going from 0, and it is again start from the 0, and it is going to its maximum value. It is clear that the output current from its maximum value, it is going to the 0, and again from 0 it is going to its maximum value. If the value of the inductor is less, so means there is a discontinuity of the current. So this is called the discontinuous mode of operation. So we have a least amount of discontinuity when the inductor value must be greater than T2 by 2 into R. This is the minimum value of the this is the value of the inductor for the discontinuous mode of operation. So we can write that T1 is equal to V0 by FVI and I0 equal to P0 by V0. So substituting the value of T1 and I0, we are finding the value of L, that is Vi minus V0 into V0 square divided by 2F Vi P0. So the equation that is this one, the equation this one, and the equation that is this one. From those two equations, if I make a mathematical calculation, we will find the value of inductor L equal to T2 by 2 into R. This is the value of inductor L, that is T2 by 2 into R. That is the conception of critical inductance in the other form of representation, but the value of inductor will be T2 by 2 into R for the discontinuous mode of operation. So the continuous and the discontinuous mode of operation, the basic difference is that the output current for the continuous mode of operation will be reaches from its minimum value to maximum value when the switch is on, and again when the switch is off, it is come back to its minimum value from the maximum value, but there is a no chance of the output current to be zero at any instant. So this is called the continuous mode of operation, and the cycle will repeats. But for the discontinuous mode of operation, if the inductor value is lesser, so the current will increase the output current from 0 to its maximum value when the switch is on, but it is again come back to its zero value when the switch is off, because the value of the inductor is lesser, and the cycle will repeat. And if as the current reaches to its zero value, we can say this is the discontinuous mode of operation of current. And this is the continuous and discontinuous mode of operation for the buck converter. Now let us take some mathematical examples in order to understand the buck converter. For a buck converter, the switching frequency is 50 Hz. On time is 1 second. If the average value of the output current is 30 ampere, find the average value of the input current. So in case of the buck converter, the output voltage, that is V0, is dVi, that is nothing but the T1 by T1 plus T2 into Vy. So we can write for constant power conversion, that is for no loss converter, the input power is equal to output power, that is Vi Ii is equal to V0 I0. So we can write from these two equations, that is Vi by V0, that is equal to I0 by Ii is equal to 1 by D. So Ii, that will be D into I0. Or in the other words, we can say that D, the duty cycle is T1 by D into I0, that is equal to T1, 1 by D equal to F, the chopping frequency, into I0. So in this case, the I1, we have to find the average value of the input current, that is T1, that is given is 1 millisecond, it is equal to 0.001 second, that is the on time. Chopping frequency is 50 Hz, and the output current is 30. So the value of the average value of the input current is 1.5 ampere. So let us now take another example. For a buck converter, the input voltage is 100 volts. The load resistance is 20 ohms and the inductance is 100 millihenry. If the switching frequency is 500 Hz and the on time is 1.0 millisecond, for the average source current of 3 ampere, find average load voltage, output current, output power, the minimum value of inductance. So we all know duty cycle is, so the chopping frequency or the frequency of switching is given 50 500 hertz. So time period t equal to 1 by 500 or 1 by f, that is 0.002 second, that is 2 millisecond. So the duty ratio, that is t1 by t, that is t1, that is on time, is given 1.0 millisecond. So 1 by 2, that is 50% or 0.5. So first problem that we have to find the average output voltage, that is V0. So the average output voltage, that is equal to D into Vi, that is 0.5 into 100, that is 50 volt. The output current I0, that is II by D, that is II, the input current is given 3 ampere by 0.5, it is equal to 6 ampere. The output power that we have to find, that is P0, that is V0 into I0, that is V0 is 50, that is given. The V0 value that we have obtained, that is 50, and I0 that we have obtained 6, so 50 into 6, that is 300 watt. Now, what is the value? The last one is the minimum value of the inductance. So, what is T2? T2 is T minus T1, that is 1 minus 0.5, that is 0.5 millisecond for the discontinuous mode of operation. The value of L2 that we know, L that is known to us, that is T2 by 2 into R. Just putting to each value, we will get the value of L equal to 5 millihenry. So this is a problem that we have solved. It is related with DC buck converter. DC to DC buck converter, or we can say it is related with buck converter, some of the numerical problems that we have seen. So we have discussed about the continuous current mode of operation and discontinuous current mode of operation related with the buck converter. Continuous and discontinuous current mode of operation of buck converter. Thank you.